As we saw in the earlier session, repricing gap analysis measures the level of a bank's exposure to interest rate risk in terms of the sensitivity of its net interest income (NII) to interest rate movements over the time frame considered, which is usually 1 year. Duration gap analysis, on the other hand, measures the level of a bank's exposure to interest rate risk measured in terms of the sensitivity of the market value of the firm's equity, MVE for short, to changes in interest rates. Please recall, market value of equity is the number of equity shares issued by the firm multiplied by the market price per share. In the forthcoming session, we will look at an example of duration gap analysis. But right now, let's do a quick recap of duration and how it is measured. Essentially, duration measures the sensitivity of a bond's price to changes in interest rates. There are many ways to compute duration, but the most commonly used ones are Macaulay duration, developed by Frederick Macaulay in 1938, and modified duration. Just to recap, the price of a bond is equal to sigma t equal to 1 to n Ct divided by 1 plus I to the power of t plus Fn divided by 1 plus I to the power of n, where Pb denotes the present value of the bond or the price of the bond, Ct is the coupon payment in period t, Fn is the face value to be paid at maturity, T is the period in which the cash flow, that means either the coupon or the face value of the bond, is to be paid out, I equal to yield to maturity, and N is equal to number of periods to maturity. Let's look at a spreadsheet to work through the price of a bond. So here's a bond whose face value is 1,000, coupon rate 6%. So the annual coupon payment is 60 every year through the 6 years of the bond. And in the 6th year, the principal will also be repaid to the bondholder. Now, this column is the present value of all of these cash flows that will happen in year 1, 2, 3, 4, 5, 6. So how did we arrive at this? 60 divided by 1 plus 0.06 to the power of 1. So that's how we arrived at that figure of 56.60. The same arithmetic is used across the board, and if you total this up, you get 1,000, which is what is reflected in this cell. Now, it is 1,000 because the yield to maturity is the same as the coupon rate of the bond. Let us say the interest rate in the country goes up by 1%. Fair to assume, therefore, that the yield to maturity for this bond will also go up by 1% to 7%. Bear in mind, the coupon rate still remains the same. Now, what did this do to the price of the bond? With an increase in interest rates, the price of the bond would reduce. Similarly, in that environment, if interest rates had gone down to, shall we say, 5% from 6%, you will find that the price of the bond sells higher than the face value of the bond. This is the principle of bond pricing. When interest rates fall, bonds will sell at a premium, and when interest rates rise, bonds will sell at a discount. That's what we have reiterated by looking at this spreadsheet. Let's extend the above bond pricing example now to compute Macaulay's duration. The formula to compute Macaulay's duration is on your screens right now, where Ct is equal to the coupon payment in period T. T is the period in which the cash flow, either the coupon or the face value is received, Fn is the face value to be paid at maturity, N is equal to the number of periods to maturity, I is the yield to maturity, and PB is the present value or the price of the bond. If you examine this equation carefully, it is very similar to the bond price formula, except that Ct in the numerator is multiplied by the period term T, Fn is multiplied by the period term N, and the whole term is divided by the price of the bond. So it is derived from the bond pricing formula. We will now use the same bond price spreadsheet to compute the Macaulay duration of the same bond that we worked on earlier. What we have here is exactly the same data that we saw a little while ago to compute the price of the bond. And what we have added here is these cells which will help us compute the Macaulay's duration for this bond. Now let's make a comparison between these two. The coupon payment is identical in both, and obviously the present value computation would be identical in both. The additional column is the year into the present value, and this is because of the definition of Macaulay's duration. Macaulay's duration is arrived at by dividing the sum of the present values of the cash flows in column K, which is this, by the current bond price. So the sum of these is 5212.36 divided by 1000, which is the current bond price. So you get a Macaulay's duration for this bond, which is 5.212. Now let's take a situation where in that country the interest rate moves up, and therefore the yield to maturity, as we saw in the bond example, would, let us say, go up to 7%. What this does immediately, because of an increase in interest rate, the bond will now sell at a discount, which is 952.33. And not surprisingly, Macaulay's duration has also come down to 5.190 from the 5.21 that we had earlier. Let us take a situation where in that country interest rate comes down to 5%. Remember, we started with 6%, so we expect the bond to trade at a premium, and therefore the figure, as we would expect, is 1050.76. And look what happened to the Macaulay's duration. It went up from 5.21 up to 5.234. Hope that spreadsheet example helped you recap bond pricing and how Macaulay duration is computed for a bond. Next, to understand how modified duration is computed, please go to the web link listed after this video. In summary, Macaulay duration estimates the weighted average term to maturity of a bond's cash flows, whereas modified duration helps investors understand how sensitive a bond is to changes in prevailing interest rates. By multiplying a bond's modified duration by the change in yield, the investor can estimate the percentage price change for the bond. In the next session, we will look at how duration is used to assess interest rate risk. For that exercise, we will only use Macaulay duration, not modified duration.